Hey guys, I'm starting this live a bit before the moment, a bit before the time we agreed, because I always like to start when there's still some people around before they go, and when they come back they lost like 10, 15 minutes. So in previous episodes we have some problems with technical issues, either sound or connectivity, so please keep me in the loop, okay? So those who are there, use the chat to keep me informed, okay? I start a bit before, and I start talking about the repositories I host at GitHub. So by the time we're really meant to start, people who are a bit behind, they're already here. Okay. So I'm Leonardo Bezerra. I'm a professor at Natal in Brazil at the Federal University. The institute is called Metrópole Digital, or Digital Metropolis. I teach two set of courses. One is for computational thinking, problem solving, and programming languages. And there are some repositories here. Well, if the broadcast is international, that's why it's in English. But maybe some people are from Brazil and speak Portuguese. If you do, there are three repositories that are interesting for that. So computational thinking with Python is like the first steps into programming and programming with Python. That advances a bit into computational thinking, which is like unplugged, so it's agnostic of what you want to use to run I mean, it's just exercises that will help you understand and improve your problem solving abilities, especially when it comes to decisions and repetitions. And then Python TADS, which is the last one, which is about abstract data types and how to solve problems using that. Okay, so it's always about problem solving, it's just scales as to how. And then the other set of repositories is the ones that we're having for machine learning and data science. So data science 0, this one's still in Portuguese. It's all about Medium posts for on topics related to data science. Panda 0 is the one I'm using for the broadcast on Tuesdays at the same time. So it's about pandas. Pandas is like the most used machine learning data science library in the Python community. If it's not, it's probably I mean, I cannot recall any other that is more used than pandas. And also the Python data science community is quite large, so that's interesting. So you're learning this, and there's one catch, which is that I prepared it so that people who don't code can learn, right? So you don't need to know anything. I mean, you don't need to know anything about conditionals, repetitions, procedures, or anything like that. It's basically just you write in a programming language, but you don't need all that programming logic. Okay, it's what we call command line interface. You know how to provide instructions, and you know what those instructions do, but you don't need really to be a coder. So that's running on Tuesdays. It's in English. Most of the notebooks are, at least. And scikit-0, which is the one we're going to use today, has been already from scratch prepared in English. So it's about machine learning in Python, again, for people who don't code. So it's quite a challenge because, I mean, I'm using just the things that the only requirement for scikit-0 is that you have tried Panda 0, because at Panda 0 we were growing up with the idea of coding without knowing how to program. And it's the same thing here. So here I'm expecting that you already learned things from here, right? So if you have some questions, that would help. So let me go here to scikit-0. And in scikit-0 you have, like, for now you only have the link for the English version. In the future I hope we're going to also have a Brazilian Portuguese version. There are people who are going to translate that. For many of these, they're already like the broadcast from previous weeks, so you can watch on YouTube. Okay, so over the past weeks we've covered the first steps with scikit-learn, then some data preparation with talking about outliers and imputation, again data preparation but talking about transformations, and today we're starting feature engineering. So we're going to be discussing feature selection, and I'm already preparing the feature extraction collab for next week. So at least these 5 broadcasts I want to make sure that we run them, and I hope I will find the time for us to have more broadcasts. Okay, but of course it's super time consuming, and I hope I can make it because I'm hosting 4 broadcasts per week and it's been crazy. So let's start here. So Colab is an interactive environment where you can run Python code and you see the output in a kind of a graphical way. So when you launch it, you can click here on connect, and you're actually connecting to a machine, to a computer in Google's infrastructure, whatever that is. So whatever that is, you're connected to a computer. You don't get access to the whole computer. Your application is what we call sandboxed inside a container. So it looks like a computer because you can see here like you have RAM, you have disk, and it's quite a lot. But it's just a container, right? It's just a sandbox. Your application is going to run inside this. And basically, when you get to the point of running, people are not going to see your code and your data, even if you're using the same computer, because things are inside containers and you're not going to see things from other people. So if I click here on files, I can see the files that you have, and these are only files corresponding to your runtime. You don't get to see files from other people. Okay, so let's talk about feature engineering first before we dive into specifically into selection. And in previous notebooks, we were talking about the machine learning pipeline. So first of all, machine learning is a specific step in the data science process. You don't get here the first time you see the data. You have to to understand the data, to be working with the data, to have explored the data. You have to know what kind of question you're trying to answer. I mean, there are a lot of things that come into play before you reach the modeling stage, which is the machine learning stage. And then for the machine learning stage, we also talk about a pipeline. So many people jump right away to trying to predict things using an algorithm, an estimator, but that's not what we do. What we need to do is that we have to have a pipeline, and in that pipeline you have to start from data preparation, where you're preparing your data in a way that the machine learning algorithms can use them. And feature engineering is the step between preparing the data and estimating and predicting. Okay, how does that happen? Well, basically there are a few possibilities. One is that you have too many features, and if you have too many features, you would like to reduce the number of features, and that's something that you do with some feature engineering techniques. Or you want to enrich your data. The data that is there could be made more interesting if you added more things, and you can produce new features. And a third option is that the preparation that you did with the data is not enough, in the sense that you could transform still the data in a way that provides features that are more understandable for the algorithms you're going to use. Okay, so let's see the two basic types of feature engineering approaches, which are selection and extraction. Okay, let me increase a bit the font size here to see if it helps. So we have selection and extraction, and here the idea of selection is that you're selecting a subset of the original features. Okay, no new features are produced, you're just selecting from the original ones. And in the case of extraction, you're producing new features. Okay, so this is something we have to keep in mind. When you talk about extraction and you're talking about producing, it might sound strange. There's going to be a notebook only focusing on feature extraction, and we're going to have that discussion there. But for now, let's focus on feature selection. Well, the idea that they're put in this order here means nothing in the real world. They can be used in either order, first selection and extraction, or vice versa. And you don't have to use both. You can choose to use only one or both. Of course, in some situations, it could be even that you don't need to use any. But still, we are learning all the possibilities here because the problems that you're going to face will demand that you know a large set of tools, right? A rich set of techniques. And ideally, you should be able to have all these tools at hand and see what turns out to be the best option in your contest. We're going to be talking about three categories here: filter, wrapper, and embedded. So let me show you a bit the table of contents here. So filter approaches, wrapper approaches, and embedded approaches. By the way, it's called just called embedded selection. I probably fixed this to make it uniform. And in the end, we're going to have a critical discussion on these topics, okay? So let me start loading the data, and as soon as I load the data, discuss the data, I'm going to stop and ask if you have any comments. By the way, if you have any comments or questions or something is not very clear, you can already start typing there, because there's a 15 to 20 second delay in the transmission, like latency. So I only see what you're writing. I mean, when you write, I can see it right away, but what I'm talking here takes a bit long for you to listen. So when you start writing, it's like 15 or 20 seconds after whatever it is said, okay? So you can drop your comments in the text, in the chat, and I'll reply as soon as I can, okay? So let's import the basic libraries, pandas and seaborn. If you missed these chapters, oh, by the way, sns.set to put into place the default configurations from seaborn. If you miss those things here, thanks, the feedback on the connection is okay. So if you miss those steps here, you can always check on panda 0, okay? We're going to use a dataset that is provided by scikit-learn. It's called the Boston dataset. And every time you run for the first time, you're gonna get prompt if you really trust what you're doing. In this case, I do. I wrote the code. The characteristics are provided in this attribute here, which is in short for description. And then it's a Boston house prices dataset, so it's price prediction. Price is real value, so we're talking about a regression problem. We have 500 instances of 100 samples. The number of attributes is 13, which is not much, right? The median volume is attribute 14, and this is the target. Usually you're targeting, like predicting the median value. And there are different ways you can get. There's one thing that is really funny here, which is missing attribute values none, which basically means this is not a real world example. I mean, when it was collected, someone cleaned it in a way that it was made perfect, in the sense that you're not dealing with missing values. Anyway, I think it's something that we can use here just for us to understand what is the point. And when we get the data from scikit-learn, we have to split it into x and y. And we could have done it directly with parameter, with an argument when we were asking for the data, but then you miss some of the information that we want to keep. So I'm saying take the attribute data, which is the input features, and convert it into a data frame. I'm going to call x, following the convention we've been following. Columns are going to come from the Boston data.feature name. So this is the attribute that holds the feature names. The target feature is accessed using the target attribute from the Boston data that we got up there. From x, I can get the index. The indices will match from x and y, and the name of the series is going to be median value, okay, which is already the convention that we have here. So median value, I'm doing it here. So I created x and y. X looks like this, y looks like this. So you see that all of these are numerical values. So let's talk about these things here. So first, this is super simplified because we are only talking about numerical features. Second, there are no missing values. Third, we're only talking about 13 features. And you might even be wondering why am I applying feature selection to select a subset of features if I only have 13? Well, we're trying to balance things here. In previous collabs, we've been using very, very large data sets. So now I'm bringing it back a bit. So I'll be alternating between data sets that have more or less features. And eventually, what I would like to do is to build the whole pipeline. And every time I'm showing an example, I can show how does that affect prediction in the end. But that is a very complex task, and I cannot do all of that in a single notebook, right? So what I'm doing here is that sometimes I'm simplifying so that we can focus on the techniques. But for sure, this is not Iris, even though it's not that big. But still, 500 samples, 13 variables, and it at least brings us another perspective on, more data sets that you get to know, right? So y is here too. Do you have any questions or any comments on this first part? Especially these things with like getting datasets from scikit-learn and stuff. This is kind of standard, right? So if you check the module datasets in scikit-learn, they have several load this, load that. The load followed by the name of the dataset you want to load. And once you load it, you get the data with this description attribute, data, target, and feature names. Okay, so it's a convenience that in general we're not going to be using much. I'm using here just get a bit of a break from Kaggle because we use Kaggle twice in a row. So I'm here using, even if it comes with scikit-learn for convenience, but this was from UCI, which is another very popular machine learning repository. I usually avoid UCI because the datasets are, I mean, everybody's been using them, so you might have seen these examples before. And the other things that datasets are not very large in general, but I think every now and then it's nice to alternate between them. Okay, so any comments? Can I move on? So I'll move on. If you leave any comments on the chat, I'll stop and I'll comment on that. Okay, so we're going to be talking about filter, wrapper, and let me fix this. It's supposed to be embedded approaches. Okay, so this is what we're going to be discussing. Let's start with filter. Filter are the most simple one. They are based on thresholds. So you set a threshold based on some of the properties that a given feature has. So a given feature. So the idea is that let's start with missing values. If I want to say I'm only keeping features that do not have missing values, I could do that. So I'll just use, let me show here. You just need to use x.drop and x is 1 to say features, and how you set to all. So if all values are no, they're going to be discarded, but there's no missing value here, so this doesn't work, right? So if I wanted to go for this, we already did it before, it's quite easy to do. The other extreme would say any, so discard any feature that has any missing values. Never do that in real life, because in a real data set, it's very unlikely that you get features without any missing data. So usually we go for all. But what we can also do is that we use this thresh parameter, which is a short for threshold. And basically what it says, I'm here getting the number of samples and saying, so it's an absolute value that it requires. So I'm calculating like 10% of this. So if it doesn't have at least 10% of non-missing values, I want it to be dropped. Okay. So of course, if you don't even have 10% of values there, it's probably, well, it might be important, but in general, you're talking about something that is very extreme, right? So it's not unreasonable to say I'm discarding things that have more than 90%, right? So more than 90% of missing values. A note here, you cannot use this with machine learning pipelines in scikit-learn. You see that is a pandas method, so you have to do this when you're exploring your data. Generally you would do it there, or if you want to do it here just before, if you want to do it here just before the pipeline, you can also do that. Okay. A second example is based on variance. So you can do the same thing we did for no values or for missing values with variance. So let's check the variance for our features here. And what happens is that the variances are in different scales, right? Because the original feature had different scales. Let's start reducing them. And one thing is that the variance threshold which we're gonna use to select, it basically uses a fixed absolute value. So you cannot say like 10%, 20%, because you don't know what to refer to, like we did here. So here we had the number of samples. Even if it takes an absolute value, I could calculate based on a relative measure. And here I cannot do that because I have different scales for all the variables. So if I try to set an absolute value for all of them, I'm gonna get the wrong results. For instance, in the beginning I was using 0.1, thinking I was talking about 10% of the variance, and I was discarding these two here. But actually it's not that they don't have variance, it's that their scale is very small, right? It's just that. So what we can do is that we can use the data preparation resource that we used before, the standard scaler. So we set everybody to the same range. We set them to unit standard deviation, and that means that if the standard deviation is unit, then the variance is also unit, because the standard deviation is the square root of the variance. Okay, so if one is 1, the other needs to be 1. So then we can set the threshold to 0.1, because we're saying that I want to keep 10, they have to have at least 10% variance. And let me just discuss a bit why you don't want features with low variance. Basically, you're trying to separate the features in a way that helps you predict things, right? Especially if you're doing classification. So if all the values, all the samples have the same value for a given feature, how is that helping you classify anything? And that's why if in general, when you use the variance threshold and you don't set any parameter, you're discarding any variable, any feature that does not present variance, right? That's what it does by default. But we can also do this, which we're doing here. So I'm going to prepare a pipeline like we did before. So I'm getting min-max scalar and standard scalar. I'm getting variance threshold, and I'm making a pipeline, right? So variance threshold, I'm going to configure it for 0.1. Now that I have a variance of 1, that means 10%. I create a pipeline where I'm adding min-max and standard scalar and doing the var selector here, right? And then I can fit my pipeline. I'm gonna get the names of the features using a mask. So the selector doesn't return to me the names of the features. It returns a series where it says true or false. True in case the feature got selected, false in case the feature didn't get selected. So when I use this mask to the columns attribute of X, I get only the columns that got selected. Okay, so this is what I'm doing. I'm not adding this to anything. I'm wrapping them up in a data frame just for you to see it. So I did fit and transform in separate steps because I wanted to get, after fitting, I wanted to get the ones that got selected. Okay, so when I do this, I see that, oh, everybody's still here. So at 13 columns, there was no one that had less than 10% variance. I can even check this if you want. I mean, of course, the problem is that I transformed and I didn't save it here, so it's a bit more tricky to do it. But what I could do is I add this to something like data transformed. Just a second. Let's keep this organized. And data transformed. That's how we can see it. But when I check data transform.var, no variance should be, see, it's all around 1. Now that I think about it, this is not working. Because now I set everybody to have a variance of 1. So if I did that, I cannot say that I'm gonna get 0.1 because everybody's at 1. That's a nice finding. I didn't know that. So this is one thing I'm gonna review here. Okay, so one of the things I have to review is this. For sure, standard scalar would not work if they didn't have any variance, because there's no way you can get a data that does not have variance and make it unitary, right? But since everybody's going to unit variance, now I'm not seeing very well how to check this. I'm gonna go back to this later and I'll try to bring you some answers on this, okay? That's interesting. So let's go for wrapper approaches. Well, safe for that question. Do you have any other question that you would like to ask? Because I understand like the missing values worked, but the variance, what I would have to do here is that basically doing what I understand from here is that it doesn't matter that I did this, because when I did this I completely canceled out the possibility of setting a limit that I could change it. So problem, this is the case where you would like to do the min max and center the mean, but you would not like to change the standard deviation. That could be a possibility. So let's try to see it's with std equals false, and let's see what would happen here. Oh, only 2 guys got left. Oh, because they're the only guys who have variance like this. I have to study this in more depth to see what is really going on, because now when I did these transformations and I didn't touch this, I have to see what happened to the variances before, because it's not really expected that you only have 2 things like this. So this is something I have to check, okay? So I'll check and I'll bring it back to you on the next broadcast. But anyway, now I have something to check too. No questions asked, so I'm gonna move on to wrapper approaches. So this family builds models to understand feature importance. That's why they're called it wrapper, because they're wrapping model fitting, okay? So wait, you're fitting models, but you're still in feature engineering step? Yep, that's why it's called wrapper. You're using an auxiliary model fitting, which is not your primary model fitting. You're using an auxiliary model fitting to help you understand feature importance. They can be uni or multivariate, which is basically a statistical way of saying they rely on a single feature or on multiple features, okay? So if I only take individual features, we're talking about univariate selection, and the kind of model that you fit is based on statistical tests. Okay. So João Vitor has a question. I don't get it. Since you are using the standard scalar, you can't filter features by variance. Let's see. So the first possibility is I'm using the standard scalar and it's setting everybody to the same variance. So when this is not set, it's setting everybody to the same variance. How can I filter by variance if I set everybody to the same variance? Okay. Even if you say, it's yeah, sure. You're saying you can't wait for the next broadcast. I understand that. So what is going on here is this. I'm losing the variance from the equation because I'm setting everybody to have the same variance. When I set this to true, everybody now has the same variance. So I cannot distinguish them anymore based on variance, right? At least that's my interpretation, because by the way, that's what happened. We printed the variance after. Let's see it again. And everybody had the same variance because you set everybody to unit variance, right? Everybody has the same variance now. So there's not much you can do. That even brings me a question for the next broadcast, but still. So if I don't set this, I'm changing the mean, right? Let's see here, I'll be changing the mean. But now I'm not changing the variance. Good question. Maybe you could use only min-max, filter by variance, and then use the standard scalar. I want to answer that question, but first I still want to see if changing the mean, zeroing the mean, is making something. But it's not supposed to, because when you're saying you're centering the data, the only thing you're doing is that you're subtracting everybody from the mean to say that is it going to have zero mean. Having zero mean affects nothing in the variance. So using the standard scalar like this is not compromising what we're doing, okay? So what is surprising for me is that here we're seeing that the variance 0.1 is already considered too much. So what I would probably do here, just for us to see, is that I'll leave the variance like this, so we see the variance for everybody. Let's see what was the variance. You see the variances are very, very low, okay? They are low. And they're different for each of the features. But now the scale is much, much similar. So I would check here, how can I translate the idea of variance into this, okay? I'll check how to do that, and basically what we're saying here is that only these features have a variance above 0.1, okay? So I would have to check, for sure, this is referring to the scale of the data. not to the percentage of variance. And this is something I was trying to understand, so that's why I'm saying I'll try to get back to this the next broadcast. But did you understand the basics? Like, the problem is we were fiddling with the variance. Fiddling with the mean is not a problem. Fiddling with the units is not a problem. The biggest question here is, how do you deal with the variance? If you check scikit-learn, it has an example for a Boolean variable. That doesn't help us here, okay? So what I was trying to avoid is that we would have to filter with specific thresholds for each of the columns, and that wouldn't make sense. That's why I'm trying to find a way. So I'll try to find a way, and I'll bring it to the next broadcast, okay? So give me feedback if that's fine. And I'll go back to the wrapper approaches, and if it's not fine, I'll go back to filter again, okay? So, univariate selection is done using statistical tests on individual features. Test scores are used as measures of feature importance. You can basically use relative or absolute number of features to be retrieved. So if you're doing absolute, you're using select k-best. If you're doing relative, you're using select percentile, okay? Great, you got it. I still didn't get it, but I will, and by next broadcast I'll bring it, okay? I only got the problem, I don't understand, I still don't have the solution. From scikit-learn feature selection, let's get select k-best, and let's use these statistical test. This is specific for regression, there are others specific for classification, right? And there's more than one option for regression, really, this is just one. K-best selector, let's select K-best. I'm providing this metric, and I'm saying please select the 5 best, okay? Because these metrics are trying to model how the target variable relates to the feature, the input feature you're talking about, you have to provide X and Y, okay? And then again, we're gonna use the idea of get support to see what are the columns that are staying. When I do this and ask for the 5 best, I got this. Why did I get this? Because that statistical test of regression is based on the idea of correlation. So let's look at the correlation between these features and the target variable. We've discussed this kind of plot before. If you missed this, Panda Zero has a good discussion on this. This is a cluster map, and here I'm talking about the correlations between all features, and I included the target variable here because I'm interested in this column here, column or row, it doesn't matter, it's a metric, right? So in this column I'm seeing all of the features that correlate to the target variable and how they correlate. Let me zoom out a bit so I can see all of them. Yeah, that should be enough. So if you see the ones that have maximum value, and here I'm talking about absolute value because it doesn't matter if it's positive or negative. Positive or negative are only talking about the direction, okay? If it's inversely proportional or directly proportional. So RM has the highest correlation, next is, sorry, LSTAT has the highest correlation, next is RM, then PT radio, then Indus for industrial, and text. These are the 5 that correlate the best, and that's why the 5 features we get are exactly this, okay? Let's go to the next thing, which would be, we could have used it instead of that metric, we could use this metric called mutual info regression. Again, it's for regression, there's a version for classification. And when I use this, it's gonna, so here I'm saying that I want a percentile. I don't want k-best, I want a percentile, so a relative number. I want 50% of my features. I run this and I get this, which are, lastly I had said 5, here I said half, so I had 13, it gave me 6, right? It got the floor of the division by 2. And these doesn't have to be a superset of the previous one, right? So industrial, RM, tax, and PT ratio and LSTAT are here, and it actually already also included NOx, okay? Anyway, if you go to the reference, the documentation on scikit-learn, you're gonna see that you have The same thing, mutual infer regression you have for classification. F regression you have F classification. And for classification you also have another one called chi-squared. So these are based on statistical tests to help us understand how these features individually relate to the target variable. So although I'm getting a lot of them, I'm analyzing them individually, okay? So I individually assess all of them, then I rank them and take them, okay? So that's why it's called univariate. Multivariate, again, this is a statistical term just to say we're taking multiple features into account. We're gonna build models, auxiliary models that are based on multiple, potentially all features at the same time, okay? This can be done at a one-shot pass or iteratively. So let's see how they differ. One-shot is the idea that I'm gonna fit a model once. I'm gonna check the importance of the features for that model that I built, and based on that I'm gonna rank them and take the ones I want to take. So we use the select from model class, and we need an estimator, right? And there's a characteristic here from scikit-learn that you can only use models that somehow provide feature importance. One of the most used is random forest regressor. I'm gonna show you some others here. So random forest is here, extra trees, lasso, SVR and SVC, logistic regression, they're all here, okay. And then what we'll have to do is I'm providing a model feeder. The model is going to get fitted inside select from model, inside the selector. And then I'm going to see, that's why again I have to provide the target variable, because I'm trying to make a model predicting with X as input the target variable, the target feature Y, okay? And based on that, I'm going to see which ones the select from model will give me the best. So select from model has some default parameters, and because of their default parameters, it's only giving me back two, which are RM and LStat. They were the ones that highly correlated, right? RM and LStat. But possibly that's brutal. I didn't want to come from 13 to 2. Let's see what we can do. So select from model provides a threshold we can configure, and basically that the default version is saying I want everybody which is above the mean importance, the mean feature importance. So it computes feature importance for all of the features and says the mean is here. I'm only taking the ones that are above the mean. So you can see that these two are kind of like outliers because they brought the mean very high so that only those two are above the mean. Okay. What would happen if we use median instead of mean? So I want to rank all the features according to their importance, calculate the median, and take, will be nearly half, right? Of course, if you have ties, it doesn't have to be half, but in principle, you expect half the features. Let's see what would happen. I'm only changing this. The threshold is going to be the median. Yep, now I got 7, so it's a bit more. So before I asked for half, I got 6. Now I got 7. And then we have Nox, which I already showed up before, RM, text, PT radio, LStat. We got this and crimp. This, let's see what they mean. Sorry, this means weighted distances to 5 Boston employment centers. So the employment centers make a difference, the distance to them. And crimp is per capita crime rate by town. So random forest regressor thinks that these are important to their prediction, okay? So this is what we call one-shot selector because we're fitting one model and we're selecting all the features based on that single model, okay? Again, I could say I don't want that many. Even if I am using the mean, I want to set max features to 5. To say at most I want 5. And then who gets kicked out? Industrial gets kicked out. Industrial? No, PT radio. Industrial never showed up here. Tax showed up. And tax and PT radio went away here. Okay? So this is how we play with select from model. You see that there are some parameters you have to configure. But it's quite reasonable, right? So this was one-shot selection. So we discussed univariate, multivariate, and in multivariate we're talking about point-shot selection. If you have questions, please write them in the chat. I will answer as soon as I can. I can see that we're having some connectivity issues. I hope it's not affecting so much. If it is, please bear with me. COVID is taking a toll also at the internet connections because everybody's connected at the same time. The last I want to show you about wrapper methods is iterative selection. Iterative selection. And iterative means I'm building multiple models. In the extreme case, I'm building a model for each time I want to discard a feature. Discard or select, okay? In the case of scikit-learn, it only provides discarding, which is this idea of recursive feature elimination, right? So nice, I didn't know there was this function. I was using feature importances and then choosing manually. Welcome to the jungle, that's what I'm saying. I cannot use a loop. I cannot use decision structures. I cannot do any of that. I'm stuck with using all the high-level things that these libraries provide. And this is awesome because I'm learning how to do things in a way that I don't have to be doing in a manual way, right? And especially because by doing it like this, you can feed things into a pipeline. Always remember that pipelines are the holy grail in scikit-learn, right? So great that this was a contribution, right? So in the case of iterative selection, which I was talking about, what we have is that we're discarding at each iteration. So every time we want to discard features, we fit a model, we check the importance, and then we discard them. Just a side note here, the original version of this notebook was written by a student, and he did exactly that. He made this big loop where he was checking the importances and iteratively discarding and fitting new models. And every time I look at something that has more than like maybe 2 or 3 lines in code that is either scikit-learn or pandas, I'm looking and say, yeah, there's another way to do that. For sure someone already needed it, and there's something that should be more practical than that. And that's a good hint even when you're checking Stack Overflow. Many of the answers are like I'm doing by myself. Look for the answers that say, you know, scikit-learn already provides this. Pandas already provides this. Always look for these kind of answers. Always avoid the answers that say, you know, I wrote this specific function, I wrote this custom procedure. Always avoid that because that's how you get bugs into your code. Try to use as best as possible the high-level procedures, methods that are provided here. Especially because if you want to blame someone, you're blaming a big organization, right? A big community, which is the scikit-learn community. Their blame is not going to fall on you. Well, it might, but still, you have someone else to share the blame with. So iterative selection goes like this. So we're going to take RFE, which stands for recursive feature elimination. It's discarding recursively. I don't understand why they call it recursive because actually it's just iterative. Anyway, people like to mix these concepts anyway. And we're going to use lasso, which is a linear model to fit this model between the input features and the target feature. You don't have to use lasso. You can use any of these options here. I'm just varying them. I showed them a table. Of course, if you're fitting more models, and you're starting from all of them, ideally what you should do is that you should try to fit cheap models, right? But anyway, you can use different ones. I'm just using lasso here for an example. So I'm saying RFE, estimator will be lasso, fit transform, and please get me the columns that you select. Show me the columns that you selected. So this is what you selected. Crime per capita. I think this is zoning. I didn't see what RM was. So this was the distance, PT radio, and LStat. I should have checked better care first what are these things. So let me see again. LStat, lower status of the percentage of lower status of the population. That would require me googling a bit more. PT radio, pupil teacher ratio by town. That's awesome. How many teachers you're gonna have, right? Radio highways. The RM was average number of rooms per dwelling. That's super nice. That's really important, really. So What's happening here, and this is important that I highlight, is that we skipped the exploratory data analysis stage, and this is really bad. And I'm only doing this because I want to keep the broadcast relatively constrained, right? Short. So 1 hour is always my limit. We're already at 45 minutes. And fortunately we have chat, and this is good because it takes a bit longer, but it makes it more interesting. So I'm trying to balance things here, right? So I've now used lasso for iterative selection. I could have said how many features I wanted to select in total, and I could have set how many features to discard at each step. So these are also parameters you can configure. So let me run this. At the end I'm gonna get 5. Before I had gotten 6, right? So here I got 5. They should be, in principle, this should be a superset of these, but it's not assured because now I changed the step, right? So when you're discarding 2 at a time, this might affect somehow what we're doing. If you're talking about some kind of randomized model here, because I'm using lasso, that's not expected, okay? Adding wrappers to the pipeline. So every time we're trying to do this, you work with pipelines. So min-max scaler, standard scaler, the variant selector there that was doing basically nothing because standard scaler was compromising everything. So let me remove this. And iterative selector. So let me show this just for you to understand something. I want to get the column names here, and this is getting a bit trickier because I have to get the mask from this variant selector, and I have to get the mask from this iterative selector and combine them. Okay. So if I didn't use this, I would just have done that. But I even make a note here to say, come on, scikit-learn, make this easier. These should be made easier. So this is what I get in the end. What is B again? So you see that now because I'm using min-max and standard scaler, the results are changing. What is B? Let me see what B stands for. B is, oh my god, it's the proportion of black citizens by town. Oh my god, that is the kind of thing you wouldn't expect. I hope it's blocks and someone wrote this wrong, because this sounds so wrong. Oh, anyway, let's focus on, I'm always getting social impact from this kind of things. So that was brutal. So I finished wrapper approaches, we finished filter approaches. Before we move on to embedded approaches, any questions, any comments? If you can leave the messages there in the chat or comment as soon as I get the feedback from you. I'll start discussing embedded approaches, okay? So filter and wrapper approaches, consider that feature selection is something that comes prior to estimation, even if wrapper approaches are using auxiliary model fitting. In the case of embedded approaches, the feature selection is done internally by the estimator when the estimator is doing the model fitting, okay? So it's not every estimator that can do this. Some can, some cannot. And we're going to discuss the ones we already discussed before and also neural networks, okay? So some of the algorithms that can do these. So yeah, I think it's the, yeah. So unfortunately, I think we are both right and the data set is wrong. Now I'm super, I don't know if I regret have chosen this data set or if I'm just happy that we can pin the problem. Anyway. So some algorithms such as generalized linear models or support vector machines make use of penalty factors to prevent models from overfitting. That's called regularization, okay? So regularization can be done based on different metrics. One of them is what we call the L1 norm, which is just the Manhattan distance. So when you say L1 norm, it might seem a bit different. When you say Manhattan distance, maybe you even don't understand what it means. Let me show you Manhattan distance here. The reason why I didn't show it in the plot in the Colab is because it doesn't matter to me that you understand the difference here between Manhattan distance or Euclidean distance, because you would have to see internally how to do how this is making a difference between Euclidean distance, which is the green line, or Manhattan distance, which are the other lines. So you would have to see it internally to see how this is making a difference. So that's why I didn't bother so much about explaining the difference. So let me just finish this topic on regularization. I'll answer the question on recursive feature elimination with cross-validation. Okay. So first, just measuring the table below, we highlight whether you can apply it to regression or classification. So LASSO is for regression, SVR for regression, logistic regression for classification, SVC for classification. Different hyperparameters control the regularization aspect, right? Alpha is for LASSO, C is for the other ones. And there's a difference between the direct or inverse relation between regularization and the parameter. So for alpha, the higher the value, the more regularization you get. For C, the lower the values, the more regularization you get. Okay, so this is important to be stressed out. And I'm even gonna check here to make sure, because I want to be sure that this is correct. So let me just get the SVC class so we can see it. So yeah, the strength of the regularization is inversely proportional to C, okay? That's interesting. I thought it was using L2, but it's using L1, but it's using L2. That doesn't do feature selection. But in another part of scikit-learn, I'm pretty sure it was saying that it used L1. Maybe it's linear SVC. Let me see. No, default L2. That is something I'll check and I'll review this, because in some other part of scikit-learn that I was checking, it said we could use SVR. So let's just be sure. So anyway, just to be sure, just to explain here. So I think this is something I have to fix here. So I was talking about select from model, and with select from model we can do this. We can use SVR, we can use SVC because it provides feature importance. But here is where you cannot, so I'm going to remove this. And the reason is that it's not using L1, it's using L2. So L2 does not do feature selection, L1 does. So the correct would be this. Okay, so let me, of course, actually let me do this. I'll leave them here and I'll add a note that like this. So let me add the note. The note will be support by default, support SVR and SVC, use L2 norm. Remember to switch to L1. L1 norm if you're using them as embedded selection methods. Okay, I think that covers it. So let me go back to the question on recursive feature elimination. So you should use it with cross-validation instead. So let me discuss this. In principle, you should never do model fitting without taking care for hyperparameters, right? So ideally, you have to be careful about this. But the problem is, if you're using with cross-validation, in this case, what I see is that you're increasing a lot the computational cost. So I think you should do that, but you have to be aware of the cost. Here I'm showing you the simple example, just because I didn't get to the part on cross-validation. Okay, so later when we discuss sampling and we have the notebooks on cross-validation, I can come back and I can comment on this. So in principle, yes, I would be in favor of always taking care about sampling, which is what they're basically considering here. But still, I'm not going to discuss this right away, just because in the order of the notebooks, we still didn't get to explain cross-validation, okay? So I can Google that a bit before the next broadcast. I would expect that it is because if you just use RFE, you could have information leakage, so you would be overfitting the model to that data. But I'll have to check that, okay? I'm not going to jump to any conclusions right now. My hypothesis would be that. I will check if that is the case, okay? So here I was talking about how to use models that can use L1 norm regularization, and because of that, they're doing selection. I'm not showing any examples here, any code examples, just because we didn't discuss those models in detail. Okay, we're gonna come to the point where we're gonna discuss those estimators in detail. Then you're gonna understand why Lasso does feature selection, why SVR, logistic regression and stuff, how they use L1 norm to do that. But right now, I have to say that they are like this. This is the hyperparameter that controls it, and this is how you regulate the regularization aspect. Okay, so please do not mistake regularization with feature selection. L1 norm regularization promotes feature selection. Okay, but it's not that general regularization promotes feature selection. It depends on the metric. The second thing is forests. So the second group of approaches is forests. So if you ever came across decision trees, it's something we're going to see later. They're super simple. They're basically selecting iteratively which features would help you split the data best. So what you're actually doing is feature selection, right? So the problem is that decision trees are super simple, but their predictive power is not so high. So what you should do is that you should use more elaborate approaches like forests. And what you can do is that usually the best approach is based on random forest. So scikit-learn provides random forest regressor and random forest classifier. So because of the way decision trees work, and because forests are a set of multiple decision trees, what the algorithm is doing is that it's automatically selecting features for you. Okay, so that's why in that example you use random forest as an auxiliary model fitting, because it's also very good at that. Okay, and finally neural networks. So the idea in neural networks is that you take input data and you're going to feed to neurons, which are aligned in layers, and you have consecutive layers processing that data one layer at a time. The thing is, if you zero out the importance of a feature that is provided, so internally training a network means configuring its weights. Basically what that means, if a weight gets configured to 0, that input feature was discarded. Its influence on the network becomes null. So that's also feature selection being done internally by the estimator. Here I'm not discussing neural networks in depth, forest in depth, or L1 norm regularization in depth, because of the reasons I told you. This is a bit of egg and chicken, so it makes more sense to discuss this when we finally get to the collabs on these specific estimators, and then there I promise that I'm going to discuss again how this is done internally. Okay, so for now it's important that you know that these estimators do it, but how they do it, in a nutshell, I talked it very briefly about it, but I'm gonna go deep only when we get to the specific collabs. And then to conclude, a critical discussion on these. So of course, embedded approaches would be very interesting if you could always use them, but that's not always the case. Depends on the application domain, if that kind of estimator does well or not in that kind of domain. Future approaches are super cheap to compute, but they also don't give you much. And wrapper are very interesting. And what happens usually is that you're going to use an auxiliary estimator that is cheaper to compute than the one you're using for the main prediction. Okay, but they don't have to be seen as mutually exclusively options. Okay, mutually exclusive options. You can use all of them at the same time if you want. So, for instance, if you can use a filter just because it's super cheap to compute, You can use embedded for what you're doing in the end, and in the middle step you can use a wrapper. So that's not a problem. The thing is, experimental analysis play a big role in machine learning, so you're gonna come out to the best pipeline configuration when you use experimental analysis, especially based on heuristics. Okay, so that's what I wanted to discuss with you today. We are at we reached the 1 hour limit, but of course there's still time to discuss for questions and other things. So any more comments on that? I'm here. I still have time. Please let me know. We started 5 minutes before. We still have 5 minutes till 6, which is when I usually like to make sure we don't go past that limit. Connection issues all the time. I'm deeply sorry. COVID is taking a toll on everything. Okay, that's something interesting. Open Data Day Fortaleza is happening this weekend. It's online, free to join. Please, let's everybody make the most of it, okay? Thanks for being there. Let's see next week with feature engineering, and I'll try to bring the answers to the questions that remain open, okay? So, super nice. Have a nice weekend and be safe.